So take about 10 minutes to look at Abel's paper for the sample and hold circuit for the project. Try to understand what's going on for that circuit. So since we have covered that, if I have NMOS and have VDD here, if I tie the gate to the drain, what is the maximum voltage I can get at the source? What's the maximum voltage? This is the same as this, right? No difference. So what's the maximum source voltage I can get? Is that VDD minus VTHN? Why? Because whenever the source voltage is higher than this voltage, VGS will be less than VTHN. So the channel will be off. So here's the maximum voltage I can get using this gate. And what if I increase the gate voltage but keep the drain voltage constant? Here's still VDD because this is a power supply. If you do the layout, it's going to be connected to the rail forever. You cannot change it. But I can change the input. If I bias this gate at a different voltage, for example, it's a VDD plus VTHN, or slightly higher than that. Okay, so at least VDD minus VTHN. Then what's the maximum voltage I can get at the source? What you think? If I lift the voltage at the gate, am I able to pass the entire VDD over to S? Is there a chance to do that? So let's see. For example, I am able to pass the entire VDD to the source. So I'm getting VDD here. So what is VGS? So the NMOS is on, right? The conclusion here is, although if I just connect the gate to the drain and then to VD, the maximum voltage I can get at the source will be VDD minus VTHN. However, if I lift the voltage at the gate slightly over or equal to VDD plus VTHN, then I can pass the entire VDD to the source. Make sure you understand this first. Okay? If you want to pass the entire VDD to here, you need to raise the gate voltage. I mean, how is that possible? Because we already have the top rail, since you have two rails for the layout, right? Since we have been doing all the layouts, right? Things like this. Here's the inverter, right? Something like that. You have two rails, and this is supposed to be the highest voltage in the circuit. How can I get something larger than VDD? How is that possible? If I want to pass the entire VDD to here, and I have to raise the voltage at the gate. However, it's larger than VDD, and VDD is supposed to be the largest voltage in the circuit. How can I do that? No. There's a voltage doubler or charge pump. This is what we covered last week. Remember, we can boost the voltage. So we need to boost the voltage. All right. There are so many ways to boost the voltage, but normally we use voltage doublers or charge pumps, right? So we covered the fundamental structure of the charge pumps last week. Hopefully you still remember that. So now let's take a look at Abel's circuit. Keep in mind, it's important to understand what's going on here first, right? Since we want to pass the entire VDD over to the source. And the reason we want to do that is, if we're using a NMOS, keep using this page, in this way, so here's the input, here's the output. This is called a pass gate, or PG. So the counterpart of this device is a transmission gate. It's a PMOS and NMOS. So you can pass the entire ground and VDD over to the output. Here's S bar. If you're using this one to pass the signal over to out, you need a higher gate voltage to do that. Right? Because this is NMOS, right? It's not a PMOS. It's not very good at passing VDDs. But it's still able to do that. You just need to increase the gate voltage to a little bit higher. So here's a sample and hold voltage, sample and hold circuit we're going to use for the project. And it looks complicated, but actually it's not. And the purpose here is to keep VGS constant whenever it's passing signal over to the other side of the transistor. So you can see here's S. S means sampling. So this pin is going to sample the signal. So the signal will be fed into this pin. And here's the output of the circuit. And you're looking at the entire circuit, but this is only pass gate. It's being used for this purpose, you know. So all the other parts is just serving the purpose, one, to increase the VGS to a higher voltage. So it is able to pass any signal, even including VDD. Whenever the signal is VDD, it is still able to pass VDD to here. That's the first purpose, all right? First purpose, pass all the signal levels from 0 to VDD to here. Second, to keep VGS consistent, or keep VGS to be a constant voltage. Why is that, right? We don't have to dive into that concept too deep, but just let you know. So whenever you are using a pass gate to sample, you hope that VGS to be a constant, ideally VDD. I mean for VGS, not VG. VG can be higher, but you do want to keep VGS to be a constant. I mean if you tie a voltage source in between G and S, are you able to change the voltage between G and S? No, it's constantly VDD because it's a source, it's a super strong source. It's gonna, whenever there's a little difference over there, like AC or noise or anything else, it will be compensated or being canceled by the source. Since the source is gonna give you a constant DC voltage over these two terminals, and it will be exactly VDD over the G and S terminals. Right, this is the ideal case. How can we create a VDD for VGS for all the, like here's the signal, here's the output. Whatever the signal is, we just want to keep VGS to be a constant. So this is called boot strapped circuit. Because whenever, if you're using an NMOS as a pass gate, I mean, here's the signal, here's the output. Okay, just imagine this device is a faucet or a pipe, right? You just want to keep the pipe to be turned on to a certain point. You just don't want to always change it, because this can cause a lot of distortions to the signal and nonlinearity. So you just want to keep it constant. If you have something like this, you tie this to VDD, this won't be constant because when signal is varying, your VGS will be changed because VDD, the gate voltage, is a constant, and this is changing. So that's why you are getting an inconsistent VGS, which can be a problem for sampling circuit, right? We are sampling. We want to, the signal changes are tiny. You want to keep that constant, to be a constant. So this is what you want to do. And here's a circuit to implement that. So let's take a look at this circuit, how this works. This part, keep in mind, this part is nothing but a charge pump. Remember, if you have a NMOS here and a capacitor here, and here's the signal, here's a clock. That's the clock. It has different phases. It's just a clock. This is that phi? Probably phi, or I think it's phi. It's pronounced as phi. Phi bar is just the inverted clock, and because they have phi's here as well, so that's a clock in phase, and that's a 180-degree out of phase, just being inverted. Here's the charge pump. If we just do not look at all the other circuits right now, just look at this part, and you can imagine that as what I just told you guys last week. Whenever you are analyzing the charge pump, imagine that if you pull this low, it only happens at that transitioning period. Okay, when this is being pulled low, it's pulling positive charges to this direction, right? It's pulling charges down or pulling charges out from the plate, from the bottom plate. And what's going to happen is it's going to attract the electrons. Go to where? Let's do it in two ways, okay? So the first way, let's just make it simple. You can just imagine that for the capacitor in the middle, it doesn't matter, you can just ignore it. Whenever this is pulling current down or it's going low, all the positive charges will be pulled in the same direction on the two sides of the plate. You know what I mean? So when you pull one side, the other side will be pulled at the same direction as well. And where to source that all the positive charges? From VDD, right? Because here's the power supply. Whenever this is pulling charges down, pulling down, pull, right? So you can imagine all the positive charges will be pulled down to here as well from the VDD. So it's just one current flow. Only happens for that transitioning period, the edge, right? Not the DC constant. Once DC is stabilized, all the charges will be stabilized. It's not changing anymore. So for the capacitor, it's only happening at the edge, right? So when this is pulling, current will be dumped into the top plate of the capacitor at the same time. So what's the voltage will be here after that? After a few cycles, I should say. Because you have two sides, you have two capacitors, and they are out of phase, 180-degree out of phase. So whenever this is pulling, this is dumping. So it's dumping positive charges to here. I can imagine previously it's already pull charges to this plate. So whenever this is going high, it's going to add that VDD to here. So you are getting two VDD over here, which means this is a higher voltage being applied to the gate of this transistor. So whenever this is pulling charges down, what's the maximum voltage can be pulled to this node by this transistor? Assuming that we have a larger VG here for this transistor. So whenever this is pulling, what's the maximum voltage can be reached at this point? Just directly VDD, because you only have VDD on the top rail. Whenever it's pulling, right? Whenever it's pulling, the highest voltage, or whenever this is going low, the voltage being transferred from here to here will be VDD. Only when this is going high, because previously there was a VDD over here being stored, and it's not going to be able to go out to anywhere because this will be a diode. So the charges will be stay there. And whenever after, during the second cycle, when this is going back to high, it's going to add that voltage to here. So that will be a VDD plus VDD. It becomes 2 VDD. Is that making sense? So the highest voltage can be reached at this point won't be 2 VDD minus VTHN. However, it's going to be 2 VDD because I have a higher voltage here to turn this on. It's different from the one I introduced here. What's the highest voltage can be reached at this point? VDD minus VTHN, because you don't have a higher VDD. It's limiting the highest voltage that can pass through the channel. However, the reason you want to use a closed structure here is because this point here can provide a higher VG for this transistor, so it can pass the entire VDD to this point. So you are getting 2 VDD at this point. So this point will oscillate from 2 VDD to VDD. Any difference from here to here? Is there any difference from here to here? Is this symmetric? Is this symmetric? It just so biting the inverter here is doing nothing but just giving a 180 degrees phase shift. But there are just pulses. I'm not seeing any differences between these two. So what's the highest voltage can be reached over here after a few cycles? So these 2 points are going to do the same job, exactly the same thing. So here, 2 VDD, 2 VDD. Here, 2 VDD, 2 VDD as well. So it's going to oscillate between 2 VDD, 2 VDD. Always. Okay, so at least the voltage is getting boosted. We need a higher voltage than VDD, and now we're getting it. And now let's see how we can use it. Here is a sampling pass gate. It's being used to sample the signal or the data from here. So here's a sampling pass gate. And the purpose of the entire thing here is to keep VGS, because VS is changing, it's a signal, it's an input signal. It's very difficult to keep VGS constant. Because if you have a constant VG, then VS is changing, VGS must be changing. And we have to fix it. Since C, we need a bootstrapped circuit, which is ideally like this. So here's the ideal circuit, and here's how to implement it. All right, ideal circuit is to tie a voltage source across G and S to make it constant. And now we want to do it by this way. The way to do that is we keep a capacitor here to hold the charge. And whenever I turn off this transistor and turn off this transistor as well, you just block it. You can see this C3, this capacitor 3, number 3, is serving as a battery. It's serving as a battery over these 2 terminals, here and here. And whenever I have a S is varying, it's going to add the voltage or pull, it's going to dump charges or pull charges out, in or out from the bottom plate of this battery. Okay, so it's going to add or minus the signal's voltage from this voltage point. And this is a pass gate. So whatever here will be the same as here, which is VG. So what's happening is, I'm going to come back to this circuit pretty soon. So let's just write down something for you. So for M1, VGS equals to VG minus VS, no problem, right? Of course, exactly. VGS equals to VG minus VS, VG minus VS, no problem. All right, so what is VG? Here. And whenever, so for example, I already previously charged this C3 to VDD. And this is the pass gate. So this voltage will be, this potential here at this node will be passed to here. So don't look at this first. Let's just imagine this is just a wire. Okay, it's a switch, right? So I can turn on, turn off. Whenever this is on, it's going to pass this potential to here and pass this potential to here. Right, so the voltage across this capacitor is exactly VDD. So VGS, now let's look at VGS. VGS equals to VDD because the sampling circuit is adding and subtracting to this capacitor's voltage, just thinking about the same operation as the voltage doubler or charge pump, right? So the voltage across these two terminals will be VDD plus VS. VS can be minus, can be plus, doesn't matter, just adding or pulling charges from the previously charged capacitor. So that's VG. And now minus VS will be VGS. So VGS eventually will be VDD constantly. It's not changing anymore. So that's why you can see here is a signal, the V in, and that's a VGS. You can see it's tracking the signal. So the difference between VG and VS is always constant. It's VDD, always constant. So here's the result, right? So that's the result we got from this circuit, and which is desired. And this is why. Get into the details. I'm pretty sure you're confused. Get into the details. It takes time to understand this. Let's take a look at every clock cycle, see how that works. All right. This is a charge pump. No worries about the details anymore because after a few cycles, the capacitors will be charged up to VDD, and VDD is cycling in between these two voltages, and which is great. So I can have this voltage. Its voltage has been used for the following circuit. So this higher voltage, which is higher than VDD, is being used to turn on this transistor. You know, because this voltage is higher than VDD, so we want to use that one to turn on this transistor in order to pass the entire VDD to this point. That making sense? We just covered that at the very beginning of the class. Remember, if we want to pass the entire VDD to the other side of the NMOS, we want to raise the voltage of the gate. And now we have the higher voltage, and now we can pass the entire VDD to here. So imagine that whenever this phi bar, whenever this clock signal, don't think about the bar, doesn't matter, just look at this line. Whenever this data line is high, what's happening? Whenever this is high, the gate for this M12 is high, what's happening? Don't think about others, just look at M12. If I turn on this gate, what's happening for this node, for the drain of the M12? So I open the channel, it's pulling this node down to the ground, right? So it's going to give you a falling edge to this node. So imagine it's just pulling. It's pulling the bottom plate of the capacitor to ground as well at the same time. Is that making sense for now? So I turn on this transistor, it's going to pull this to the ground. Okay? At the same time, if this is high, and the voltage here is at 2 VDD. Do you agree with that? It's like a charge pump, right? So whenever this is dumping charges to the bottom plate, it's actually increase the voltage here to 2 VDD. And whenever this is discharging, it's gonna oscillate back to VDD, right? So whenever this is high, it's pulling this to the ground, and this is 2 VDD. So this is 2 VDD. So we got a higher voltage for the gate for this transistor. Whenever you are pulling this down, what's happening? Just for C3, what's happening? Think about that, okay? I have a valve. Just imagine this is a valve. And I want to fully turn on this valve. Fully turn on. Keep in mind, I want to fully turn on this valve. If I want to fully turn on this valve, and I want to dump charges to the top plate of the capacitor, I want to pull the bottom plate down to ground as well at the same time. So I can source the positive charges from VDD, and I can pass the entire VDD to this point. So I can exactly have a voltage drop of VDD across this capacitor after I'm done with that cycle. Okay? So these two are being turned on at the same time. Turn it on, pull, boom, turn it off. Okay? Turn it on, charge, turn it off. So you are going to store charges to the two sides of the capacitor, and the voltage drop across this capacitor will be exactly what? VDD. All right. Now let's look at this point. Whenever this is high, remember I still turn this to on, turn on, pull, charge up, right? Still in the same cycle, because this is the same signal as this one. So this is also on, right? So what's happening is this is on, so the ground will be passed to here. This is always on, so the ground signal will be passed to this point. So it's going to pull this to ground. So what's happening is when you are charging up, C3 is preparing for something, right? So it's charging up C3. This point is actually being reset by ground. So you are worrying, hey, if I'm resetting this point and I'm boosting this voltage, am I passing VDD to ground by this transistor? Is this being turned off or turned on? Let's take a look. So whenever I'm resetting this point by the ground, and the same cycle, I'm turning this to on and charging up this capacitor to VDD, you see this inverter is actually controlling this point. And what is this point? So whenever this is high, phi bar is high, phi should be low, right? So phi is low. For this inverter, that's a PMOS, that's an NMOS. For this inverter, phi is low, which means the PMOS is on, NMOS is off. So this is off, this is on. So VDD will be passed to this point. So whenever I'm charging up, it's still the same cycle, right? I'm charging up C3, and also I'm resetting this point. At the same time, I'm giving a VDD to the gate of this PMOS. And what's happening? If you give a high voltage to the gate of the PMOS, what's happening for the PMOS? It's off, right? So that's why you need a switch here. Is a PMOS is performing as a switch. Because when you are resetting, you're resetting this point to be ready for another cycling or sampling cycle. You want to cut it. You don't want to connect whatever charges to this point, because you just want to isolate this stage from the next stage, so you can just charging up C3 but not doing anything else. No, so the PMOSes are the ones you can see the arrow is pointing in, and NMOSes the arrow is pointing out. That's how you distinguish it. You see that? So whenever this is getting in as a PMOS, and when it's getting out, it's NMOS. So all these ones are NMOSes. It's kind of different from the ones you have used. They always have PMOSes on the top, right? This is different. So all these ones are NMOSes. NMOS. NMOS. All of them are NMOS except for this one and this one. These two are PMOSes. All right, so when I'm charging up C3, I'm resetting this point, and this is off, right? And this is 0 because I'm resetting this point. So this is 0 and this is NMOS, and whenever the gate of the NMOS is 0, this is off. So the sampling signal or the signal is not getting through this pass gate. So everything of the next stage is blocked from this stage. So I can just focusing on charging up C3 to what? To what? VDD. All right. We're done for that cycle. So VDD ready to here, right? And then this goes low. The entire thing here goes low. And this is blocked. So disconnect circuit. And whenever this is low, it's pulling charges out from the bottom plate. And so this point will be down to VDD. VDD, VDD, VDD. And also VDD. So what's happening? VDD, VDD. So VGS is 0. It's lower than VGH. So it's not going to turn on this thing at all. So it's going to be blocked. So as the next cycle, these two transistors are gone and only leave this capacitor floating in the air. This is not being connected to VDD or ground. It's just floating there and holding a VDD voltage across the two plates. Nothing else. Just floating. So whenever it's floating, and whenever you adding or minus, adding or subtracting a signal to it, it's going to track. It's going to track that signal. All right. So now let's see how that tracks that signal. So now, as we know, this is low and this is low, so it's cut the connection from here to the ground. So it's not affecting the circuit anymore. It's not resetting the circuit anymore. Okay. So this is gone. And because this is low, so phi bar is low, so phi is high. So whenever phi is high for this inverter, it's pulling this point to this point, which is lower, a lower voltage. All right. Whenever this is a lower voltage being applied to the gate of the PMOS, and this is still VDD, so VDD minus VG of the PMOS is larger than VTHP, so this is on. And when this is on, it's serving as a pass gate, so the signal here will be directly passed to this point. And same to here. So whenever this is a high voltage, this pass gate is on as well. So the entire voltage difference between the capacitor of the C3 will be passed to here, and which is exactly VGS, which is VDD. It's constantly VDD because this capacitor is floating. And whenever VS is increasing, it's going to boost the signal as a charge pump to VDD plus VS. And VG is always VDD plus VS as well. So this minus this, VG is VDD plus VS, and this is VS. So VDD plus VS minus VS will be VDD constantly. It's not changing anymore. What a beautiful circuit. That making sense? Kind of. Just record it so you can go back and look at it later if you couldn't get it for now. I have connected everything in LT Spice. You can directly use it if you like. So there's a question regarding this one. So what's the function of this circuit, of this NMOS to be here? It's always on. So why you want to add one NMOS in the middle of these two parts? Because this voltage can be higher than VDD, sometimes can be 2 VDD, because if the input signal for the data is VDD, then this VDD will be added to the previous the previous stored VDD here. So the voltage here will become 2 VDD. And 2 VDD being added to the drain of this transistor probably can blow up this transistor and burn it. So that's why you add another one to increase the resistance and have another voltage drop across this NMOS channel, so you can protect this transistor. That's the function of this guy. So what's the function of this guy? It seems like it's not doing anything. Keep in mind, the voltage here can be higher, and I'm willing to pass everything from here to here. So I can directly connect these two terminals to these two terminals. All right. But the voltage, the gate voltage for this NMOS is not high enough to do it. So I need a higher gate voltage to connect this pin to this pin, to pull it down to this pin. This guy cannot do the job because sometimes it's higher than the clock voltage high. So I need a higher gate voltage to do that. So this transistor will do the job. All right, let's look at the simulation. Yeah, I probed this point, right? So here's a voltage is being boosted to somewhere around 2 VDD, which is somewhere around 2 volts, and then come back to 1 volt, which is VDD. And what about the clock signal? So I'm going to probe this point here. And now let's see if this is making sense or not. All right. Like what I just, analyzed. Whenever this pin is high, what is this circuit doing? Whenever this pin is high. It's pulling this to the ground, right? And it's turning this on and allowing VDD to pass to this point. So I'm charging up C3 to VDD, right? That's that cycle, during that cycle. So whenever I'm turning this on, I need a high voltage at the gate of this NMOS to be ready. So here, this pin is called VE0, so which is the blue one. And this voltage is called VA, is being labeled like over here. So this is VA, which is the gate voltage of this transistor. And here's VA. Are they at high at the same time? Remember, whenever I want to turn on this NMOS, I'm pulling this down and I want to turn this on so I can transfer VDD over to this point. So it needs this gate voltage to be high. Are they at high at the same time? Yes, so when this is going up, this is going up as well at the highest voltage. So at this moment, at this rising edge, I'm able to pass the entire VDD to this point. To this capacitor. Even though it's getting lower than the highest point, which is fine because it's still higher than VDD. But I'm able to provide a voltage which is higher than VDD for this period, so I can pass the entire VDD to the top plate of the C3, and then turn it off. Right? Just shut it off. Just cut it so the charges will be stored in the capacitor. That making sense? So whenever the charges are ready, I can start sampling So because we want to verify if the VGG is tracking the signal, it's hard to see here, so I want to simulate for a longer time. What is this signal? Should take a while. Stop. And look at data. So here's the right color, the right signal is VG. This is VG, and this is the signal input, which is the data. You know, the data can be all different kind of data because it depends on the sensor, right? Because the sensor is transferring the temperature or humidity or anything to an analog voltage. We use the ADC to sample it. So here is just the signal from the sensor, for example, and has a DC offset, which is common. You can see the DC offset anywhere of the sensor. And here's the signal. And your VG is tracking that signal to make your VG minus signal, which is a VGS, to be a constant, to minimize the distortion of the sampling. Okay, so that works. If you look at signal, it's being sampled and held from the data. All right. Okay, hope that makes sense. It took longer than I expect to explain this. Still have about 10 or something, like 10 minutes. It's being used for your ADC, SAR ADC. Oh yeah, so it's a good reminder. So I just had a question for you last time. Remember that? The SAR ADC. Remember? I have, here's a comparator, here's a sample and hold circuit. I just, spent pretty much the entire lecture to introduce it. And the comparator can directly use from my website. It's from Dr. Baker's CMOS textbook. And the SAR ADC structure, you want to design by yourself. I think the deadline to do it is, to complete this design is April the 9th. And today is the deadline to finish the TI D flip-flop, set and reset. And the SAR is going to feed a 8-bit digital signal to this DAC. So the DAC can convert everything to an analog signal and being used for the comparator. My question is, we are doing analog to digital converter. It's an analog to digital converter. And we already get the digital signal after the SAR. Why do we still need to do this and eventually get an analog signal out from the entire thing here? The digital signal here for as the output. ADC, right? ADC, we need a D as the output, right? We need a D as the output. And for the Columbia University's design, remember, they got the digital signal here and then converted by another external R2R DAC, and then to drive the speaker. Why do we have to use another DAC? Not directly use this DAC's output. Do you know what I mean? That's the on-chip DAC inside the chip. Right. What's going to happen is they have to use this digital signal as a digital output, and they are going to run R to R DAC and then to a speaker in their design. And this is inside the chip. This is PCB outside. So the question is, they already have a DAC inside the chip. Why not directly use this signal to drive the speaker? You can have a driver, whatever, you can have an amplifier. But why they have to do a DAC and then speaker? Why is that? Yeah, exactly. Is everyone else getting that? Remember when you are drawing that state diagram, remember for the SAR ADC, how many states? If it's an 8-bit, SAR ADC, how many states do you need to finish the converting cycle? If it's an 8-bit ADC, how many states are there when you are drawing? No, n+1, right? 9, yeah. So you need 9 states to finish one conversion. However, this signal includes all the incomplete cycles as well. So it contains all the incorrect numbers. So you cannot directly use it to play music. You have to wait until it's ready. So there might be a control logic in between. So whenever it's ready, boom, send it. So whenever it's being received by this SAR DAC, it's a correct data to be converted to a analog signal, right? But this signal is not always ready. That making sense for the project? Have you started working on the project? Okay, great. So let's look at the schedule, just give you guys a reminder. So what's the plan for this week? Tomorrow we have a lab, and Wednesday no lecture, Friday no lecture. Take your time to complete the SAR block design. It weighs 20 points in the project. All right, this is a task for this week. And next week on Monday, I'm going to check with you guys, see if you have any good progress on this. All right. Probably not for now. Yeah. No, just do it. Mm-hmm. No. So if you are not coming to the lab, this is the only time we are going to meet this week. Right? If you're coming, then I'm going to be in the lab and help you with any issues with the lab. And Wednesday is a holiday. And Friday, I want you guys to spend time on the project. And also for the following lectures, I'm trying to reduce the number of homework assignments so I can give you more time to work on the project. Is that okay? All right, since there's some uncertainties for the design since I haven't done the control logic, right? Since there are so many other things you need to design by yourself, not just the main blocks. There are some, for example, the clock dividers and the control logic over here, maybe. I mean, I don't know. You have to think about it. I want to implement the conversion in the circuit. All right. That's everything about today.